Have you ever looked up at the night sky, at that vast, dark canvas sprinkled with countless stars, and asked yourself a simple question: are we alone? Is our little blue marble, Earth, the only world teeming with life, or even the only world of its kind? For millennia, that question was the stuff of philosophy and imagination. We had no tools to answer it, no way to peek into the backyards of our stellar neighbors, but that has all changed. We now live in a remarkable era of cosmic discovery. An age where we can say our solar system is not the only one. There are other worlds, orbiting other suns, scattered throughout our galaxy. These distant worlds are called exoplanets. The exo part means outside, planets outside our own solar system. So, how do you spot a tiny planet, often smaller than a speck of dust, orbiting a star that is trillions of miles away? It's an incredible challenge. Imagine trying to spot a mosquito in front of a blinding searchlight located in another city. The mosquito doesn't produce its own light, and it's minuscule compared to the brilliant beam. Exoplanets are incredibly faint, overwhelmed by the glare of their parent stars. Direct imaging is extremely difficult and rare. So, we have to get clever and look for a planet's effect on its star. One of the most successful techniques is the transit method. It's a beautifully simple concept. If a planet's orbit is aligned just right from Earth, it will pass directly in front of its star, blocking a tiny fraction of light. For a brief period, the star appears to dim ever so slightly. Like the mosquito and the searchlight, you notice the tiny dip, not the insect. This dip is the telltale sign, the cosmic wink that signals a planet. The change is incredibly small. For an Earth-sized planet crossing a sun-like star, the light might dim by less than 1/100%. That's like noticing one bulb flicker in 10,000. We need incredibly sensitive telescopes that stare for long periods with extreme precision. We also have to see the dimming repeat on a regular schedule. If the same dip returns every 30 days, we've found a 30-day orbit. The amount of dimming tells us the planet's size relative to its star. Bigger planet, deeper dip. Transit length reveals orbital speed, and the time between dips gives the length of its year. The transit method is powerful, but only if the orbit aligns from our view. What about systems tilted away? Enter the radial velocity method. Detect the planet by its gravitational tug. Planets and stars orbit their common center of mass. The star is massive, so it barely moves. Imagine a parent and a small child spinning. The child swings wide. The parent traces a tiny circle. The star is the parent. The planet, the child. Even big stars wobble, a tiny rhythmic dance. We can't see the wobble directly, but we can see its effect on starlight. Doppler effect. Think of an ambulance siren shifting pitch. Light does the same. Toward us, blue shift. Away from us, red shift. That back and forth shift is the wobble's fingerprint. Measure those tiny periodic shifts, and you find a planet. The wobble size reveals mass. Bigger wobble. None of this would be possible without our telescopes. Finding exoplanets needs breathtaking sensitivity, measuring minuscule changes from trillions of miles away. Massive observatories on high peaks, far from city lights, track stars night after night. Facilities like ESO in Chile use spectrographs so precise they can detect a wobble as slow as a person walking. These are the workhorses of radial velocity. But our atmosphere distorts starlight, making ultra-precise transit measurements hard. Like watching a movie through rippling glass. So we leaped over it, into space. Above the blur, the view is crystal clear. NASA's Kepler stared at 150,000 stars, watching for tiny dips, and changed everything. With every new exoplanet, the universe feels less lonely and more interesting. We're no longer guessing, we're building a real atlas. We've found hot Jupiters with years that last only days, super-Earths, rocky worlds larger than ours, and even planets with 2 suns. A real-life Tatooine. Nature's imagination is wilder than our own. This growing catalog puts our solar system in context. What's common and what's unique. Small, rocky planets like Earth appear abundant. By studying their atmospheres, we may soon search for biosignatures, gases like oxygen or methane. Finding them on an Earth-sized world would be profound. The search is a story of human ingenuity and relentless curiosity. We've gone from knowing only our planets to thousands of confirmed worlds. The question isn't if other worlds exist, what wonders do they hold?